Cool. Thank you. Okay, so as I was preparing last night the slides, I realized that there is no way I can describe all 5 projects that are part of GENI in 20 minutes, at least not to a point where people would understand really what I'm talking about. So I'm hoping that given previous talks that we had and previous IABs where we more or less talked about some of these initiatives will help us to sort of speed things up. So just to recap what Ray already mentioned, there are 5 GENI-related projects that we have. 2 of them, the 2 green ones, were what's called the Spiral 1 GENI projects. OMF stands for Orbit Management Framework and WiMAX Virtualization. And the other 3 are from what's called the Spiral 2. The first one is just a standard project, a CR kit or cognitive radio kit. And then the 2 Mesoscale deployments, which are supposed to be a large-scale deployments of GENI and involve multiple universities which are listed in here. By the way, as you can see, GENI is sort of trying to move into these large collaborative projects more and more, and I believe the Spiral 3, which Chip will probably talk about, is going to encourage that and sort of try to create these large infrastructures that people can use for experimentation. So, Spiral 1 project, and one that sort of came out of the orbit world, is the Orbit Management Framework. As the previous slide suggested, it's what's known as Cluster E in GENI, and essentially it's Cluster E is created around the Orbit framework, which is the framework for management of wireless testbeds. As you know, Orbit is about 5 years old now, and the framework itself is 6 years old, right? We first started doing the framework and deployed it after a year of work. And currently we are at version 5.2. Couple of things that sort of distinguish this version from the previous versions. I would argue the most important one is the switch over to pub-sub model, where we allow the testbed to be controlled by multiple entities and where we allow those control entities to express their interest in certain things, right? Whether it's nodes or measurements or any other resource of the testbed. And of course, immediately thing that follows out of that is the ability to run multiple simultaneous experiments. I'm refraining from calling it virtualization mainly because we still don't have a solution, a good solution for wireless virtualization. We have it for certain topological cases, but not for general wireless case. Now, things that we worked quite a lot these last year or 2 are related to 2 things: the mobility support and disconnected operation. We have a few slides following on that, as well as new types of wireless systems, and not just wireless, but others. Namely WiMAX, cognitive radios, and wired network support, which was something that was fairly new for us in orbit world. And then, of course, one thing that GENI naturally brings about is to try to tie up these different testbeds into a single homogeneous system, right? So let me start first by showing the feature of OMF 5.2, which is sort of, in our case, quite interesting, and that supports mobility in case of, especially for wireless, vehicular devices. So the idea is that in case of vehicles, right, eventually you lose connectivity with the substrate. And therefore you need to support what we call the disconnected operation. And the way we do it, we essentially download the experiment description onto the device, let it disconnect from the control network. By the way, control network is assumed in the old orbit to be always present and is used not just for control but also for measurements. And then of course, in order to do that and support the disconnected operations, we also had to cache the measurements effectively on the devices, or in this case, vehicular nodes, right? And we did a couple of demos on various GENI engineering conferences where we showed the effects and abilities of this new extension of orbit. At the moment, we are still counting on the fact that the nodes have to be always on, right? In other words, we don't allow you to turn off the device, and that actually presented an interesting problem for one of the projects that we have. So next version is going to be a persistent state of the experiment, where even if you turn the power off of the node, turn the car off, you can sort of save the state, and then once you turn it back on, you will continue from where you stopped. And of course, in vehicular cases, it might be that you have multi-day operation outside of the control framework itself. So that's why it's somewhat important. The second feature that's related to mobile support is the introduction of spatial and temporal triggers, right? And the idea is fairly straightforward. The assumption is that each mobile device has a GPS or some other way of defining localization, right? And then you can specify certain geographical coordinates at which you want certain events to happen. And so, for instance, if a vehicle passes a region on a highway, so in other words, if I create a coverage region around a section of the highway, that will trigger the event that the control framework will interpret and execute a piece of code that's associated with that spatial trigger, right? Another type of event that's sort of interesting is that 15 seconds after entering the parking lot, or sometime after entering the parking lot, you do something. And typical example is shut down the node gracefully, right? I mean, store the state and shut it down. So that is a prerequisite for that multi-day operation that we're talking about. Of course, it's not yet there, so we still have to work a lot, because it's not that easy to capture the state of the experiment completely so that you can continue after that. And then, of course, the other interesting trigger that we would like to, that we introduced, is the idea of being in proximity of some other nodes, because that might signal certain conditions that are interesting for the experiments. So, of course, most of the work went into defining these graphical interfaces that enable you to easily specify these triggers and events. The part of OMF, but not necessarily integral part, in other words, OML, which stands for Orbit Measurement Library, can be used, and it's used in quite a few cases outside of the OMF, is actually dealing with the collecting measurements, all sorts of measurements in the testbed context. And especially in GENI world, that is a fairly important part of the overall architecture. And we just had a two-day workshop in Chicago last 2 days related to instrumentation and measurements. And it's essentially dealing with things that various testbeds are trying to do in collecting measurements. Again, the OML, I guess, the OML version 2 is based on push. In other words, the sensors and devices are pushing measurements towards the substrate. We try to separate the collection process from the instrumentation itself. In other words, there is a client library that enables you to efficiently collect your measurements and separate the process of transmitting them to the server from the actual collection process. And then, of course, try to minimize the collection overhead, right? Because that's the most important aspect of measurements that we see in the real life. Again, mobility and the fact that you are quite often disconnected from substrate in mobile cases argues for doing the proxy configurations which enable us to store measurements locally before when the connectivity is lost. And this is sort of a fairly busy picture that sort of tries to explain all the features. The main idea is that we have measurement points all the way on the left that are part of the application. They're supported by the client libraries. In other words, people instrument their own application the way they think they need to. By the way, the OML, as far as what the actual measurements are, OML is completely transparent to that, in the sense that it doesn't really care what you're collecting as long as you know how to do it, right? And then you have all these filters which enable you to dynamically configure the collection process of the measurements that are streamed to the server. Again, for disconnected operation, we have the bottom case where you can store measurements locally and hopefully transfer them after the fact over to the server. As far as where the OMF is currently used, as you obviously, two obvious places, because we are doing this in strong collaboration with NICTA, is actually what we call Orbit and Norbit. Norbit stands for NICTA Orbit, right? And then quite a few places in Europe, are actually using OMF. By the way, OMF is now a completely independent project of Orbit in a sense that it's treated as even though OMF originally stands for Orbit, I think we renamed it in Control Framework for Networking Experiments or something like that. So it's now sort of has a life of its own that's not necessarily, strictly speaking, related to Orbit, but quite a few places are using it. And again, we do have an early integration of the Planet Lab in the attempt to sort of bridge these multiple frameworks. Just a laundry list of things that we are planning to do in the OMF 5.3, which is expected sometime next month, hopefully in time for GEC 8, but we'll see. And I really don't want to spend any time on this because I'm already running way over my allotment. So other than to sort of say that we are still trying to, the most important feature would be the steering of the experiments. So what we really want to do is give users the ability to use their own measurements to control the experiment itself, which is an interesting local feedback that we have to figure out how to do. Okay, the second Spiral 1 project is on WiMAX virtualization. And again, here, given that Gautam is giving a talk later this afternoon devoted entirely to WiMAX virtualization, I'm just going to very briefly go over the features. But the main idea of WiMAX was the fact that we want to provide experimenters with cellular-like system to play with, because traditionally that's the most difficult part. Obviously, operators don't really want you to play with their equipment, and researchers, on the other hand, want to break it as much as they can, right? So hope is that we can come up with a deployment that researchers can use to sort of play with. On the other hand, it's really inefficient if we sort of say give a base station to a researcher and he's the only one who can play with it. So the main idea: how do we share the base station among multiple experimenters? And that's what we try to do with the WiMAX. Just to prove, the WiMAX base station is actually sitting on the roof of our Route 1 building. Unfortunately, it's not elevated. The antenna is not elevated. It's sitting in the pit wall inside the enclosement for the air conditioner. So to make a long story short, we do have a coverage, which is, as you can see, this is Route 1, right? Which is relatively decent along the Route 1. And of course, once we move into a full production, we are hopefully going to improve that by actually taking the antenna outside of the pit wall, making sure we properly orient it, down tilt it, elevate it as much as we can. And by the way, there will be second deployment on the Bush campus, so we will have two base stations which are not necessarily going to overlap in coverage, but will allow us to do some interesting experiments nevertheless. Now, as far as virtualization goes, I'm just going to flash this picture mainly because Gautam is going to talk way more about this. The main idea is that we have a custom-made ASN gateway, which stands for Access Network Gateway, I believe, or something like that, that is connected to the base station, and NEC, whose base station this is, really is actually supporting us in the sense that they're providing custom ASN gateway that allows us to do all sorts of things to the base station itself, which you normally not necessarily do. And then, of course, we have the virtualization substrate where we divide a physical machine into a bunch of virtual machines and then give each experimenter access to one of those and pretend as if it's a base station controller in its own right. So you will hear way more about that later on from Gautam. And I really don't want to, I mean, if you have any questions on the WiMAX virtualization, we can really go into all sorts of details later. Now, the Spiral 2 project that is sort of fairly interesting as far as what we really want to do in the future is the cognitive radio kit. And the main idea there is that we really want to come up with the open source platform that researchers can use to sort of play with the waveforms, radios, policies, spectrum access, and all the other nice things that people are talking about. And of course, the cost is an issue. So one of the things that we are doing is sort of trying to use as much common off-the-shelf elements as we can. Of course, it's easy with FPGAs, and that's what we are using. And however, one of the features that we really want to sort of emphasize is the availability of three different RF front ends. The first one is nothing special. I mean, we already have it for quite a while, which is the ISM band radios, right? The second one, which hopefully will come any day soon, and I'm looking at Peter, so, you'll see the slide on it. I would argue it's fairly interesting, mainly because look at the range. It goes from 0 to 7 gigahertz, right? Even though Peter claims it goes actually to 8, but I'm conservative, so I put it at 7. And then something that's coming in the phase 2 of the project is the much wider baseband, which goes up to 500 megahertz, right? Of course, this is in the future, this is immediate future, and this we already have. Now, the thing that we are working the most, in addition to hardware itself, is the application framework. One of the big problems with cognitive radio platforms in general is the fact that they are notoriously hard to work with, mainly because they involve VHDL and a sort of fairly steep learning curve, especially for students. So the idea is to come up with a framework that makes this much, much easier. Just to flash the board, and this is last night's picture. This is the RF front-end board. As you can see, it's a fairly large complexity of the board. 12-layer PCB. I don't even want to know how much effort it went into designing this board. But the main feature is that it goes from 30 to 8 gig, and the fact that it's full duplex and switched antenna diversity. Of course, it does support MIMO in the sense that we can put up to 4 of these on the single FPGA, right? And time synchronize and phase synchronize them together. As far as the software architecture is concerned, the main idea is that we provide all the blocks except for the application itself, right? So hopefully people can fairly straightforward, whether they do it in RTL or they do it in Simulink, put their blocks together, tie it, and push the button, and everything works like a charm. Of course, it's not going to happen, but at least in some simple cases, it might work. So we'll see how far we go with that. But anyway, the framework is, and this is actually the framework that we want to demonstrate fairly soon, is sort of ready for people to take over and run with. By the way, this is a project that we do together with the University of Colorado and SDR Systems. And now I just want to quickly go over what we call a mesoscale deployments, or what GENI calls mesoscale deployments, which we are sort of part of. The first one is the WIMAX mesoscale deployment. As I said, the idea is to deploy these virtualized WIMAX base stations across 8 campuses in the US, right? And you can see them all listed there. And of course, in GENI world, they will be somehow connected, whether it's done through the internet too or through the overlay. But in any way, very soon we'll have 8 WIMAX base stations connected across with the backbone. Of course, hope is that at some point you will be able to run an experiment where you pretend to be a large ISP or virtual network, mobile network operator that has a footprint of across the country, right? As far as what KIT looks like, right? I mean, this is so we actually are now in the shipping business, right? Every other day we ship a bunch of boxes around the country, right? Say with the antennas, base stations, cables, and all sorts of other stuff. So, I mean, I just couldn't resist to put this on the screen to sort of show what it is all about. The second the second mesoscale project that we are part of is the Openflow mesoscale project. And the idea there is that we will have this programmable fabric that Masa will talk about a little bit more later on, that is deployed both in orbit as well as in production network that sort of is willing to play with the new equipment, right? And so the idea involves something that's called the ION, which I'll show in the next picture. a couple of programmable routers at key points in the university. And in our case, it's somewhat interesting because there are two campuses. The one where the orbit or Route 1 campus that's covered with the programmable fabric. And then, of course, tunneling through the core Rutgers network onto the Bush campus, where we also have, both we and CS have offices. And the idea is to create these fully programmable devices in the middle and give people access to sort of control it and play with it, right? And of course, ultimately, this is all connected to Internet 2 or an LLR, and again gives you a really fairly large footprint to play with, right? In a wired sense, not necessarily wireless. So as far as what ION has, it's essentially, and I always laugh, we are getting back to switched circuits, right? It's essentially, it gives you ability to create a point-to-point connection anywhere in Internet 2, right? So we are going back to circuit switch days, where you can sort of dial out and say, I want to connect between Rutgers and BBN. The beauty of it is that you can sort of say, and I don't think you can see it here, so you dial literally, so this is source destination, but then you also specify how much bandwidth you want. So you can sort of say, I want 50 megabits, or I want 10 gigabits of bandwidth between these two endpoints. And since you can have multiple simultaneous connections like this, you can create a fairly controlled network in this sense. And that's, I guess, why it's somewhat interesting for creating new topologies and new wide footprint networks. And so we use this, and in this particular example, we use the ION connection to connect us to Norbit. And as far as I know, this was the first time that there was a gigabit connection between our lab and our Orbit lab and Norbit, which is in Sydney, Australia, right? So you can literally dial a connection. There is a fiber path, a gigabit fiber path, which goes to the MACPA East, which is in Philadelphia, then connects, hops onto ION, which is in Baltimore, goes to LA, I believe, then hops onto the Deep Pacific Wave, or whatever they call it, goes to Australia, then goes onto their research network, hops, eventually gets to Norbit, right? Very interesting experiment, and I think they sort of proudly announced it as the first connection between US and Australia over ION circuit. And just to sort of point out what it really means is that when you dial, say, a gigabit or something close to gigabit bandwidth, you essentially can transfer a HD movie in less than 60 seconds, right? Which is a beautiful, I mean, a lot of our students would love to get their hands on this, right? Especially for downloading movies. So, and you know, of course, the main feature here is the fact that it's a fairly controlled latency link, and then you can sort of try to build, hopefully, some other networks which are more interesting than just simple TCP/IP networks. Oops. Okay, so I guess my latest version didn't come up. So I'll speak without a slide. So that would be all about the GENI projects. Another thing that I think Ray mentioned briefly is the fact that we also got the extension to our new project related to Orbit. And the idea there is that, of course, Orbit nodes are now 5 years old, and we really want to replace them. And as part of the replacement process, we are now trying to sort of design nodes for both heavy-duty computing, which is required for cognitive radio applications. And so one class of new nodes will be centered around quad-core, Pentium, fast machines, with a slight twist that the ceiling in Orbit room cannot support the new weight of the node. So I don't know how we're going to solve that. Hopefully there will be some form of solution. So nothing to do with the cognitive radios or engineering. I mean, this is real engineering, right? You want your ceiling to stay there. And then the second one, of course, is the node that's designed for mobile operations. And there we are trying to sort of put as much processing power as we can, but make sure that the typical car power supply, which is limited, I believe, to 150 watts or something around that, can still support it. We still want to be able to put a cognitive radio inside that smaller platform, but have to deal with the power consumption and power supplies and a couple of other things. So that would be all that I had to sort of say about the experimental platforms and GENI-related projects. So if you have any questions, please feel free to ask now or later. Just fetch me and we can discuss it. Go ahead.
I noticed the FP7 logo on one of your slides.
Yes, so there is
some ongoing collaboration.
Yes, so, and it's sort of a multi-level collaboration there. I'm just trying to get there. Oops, this one, right? So there is a, we had a collaboration with a project that just ended, which is called Forward, right? With European people. And then NICTA has a direct involvement in WINLAB and FP7 projects, right? So there is a multifaceted collaboration between Europe and the US. And there is even talk now about some collaboration with Japan, especially as far as OMF is concerned. Yes?
In OMF, are you still using Ruby?
Yes, yes, I know it makes you happy. Yes, sure, it's all Ruby-based, yes, absolutely. Any more questions? Okay, thank you. Yeah, I'm sorry, I went way over.